also the number of electrons in an atom. But you would never say that the atomic number is the amount of electrons, because that is not its definition. All right, so atomic mass number, which is the total number of protons and neutrons in the nucleus of an atom. If you look at a periodic table, I should have loaded one up. If you look at one, you can see that it's underneath, it's at the bottom, at least on the one in my classroom, and it's going to be a decimal number. It's not a whole number. We're going to probably work for the most part in whole numbers, but the reason why it's a decimal point, if you guys remember this from 10th grade, that you have isotopes, so you have several different kind, and it talks about that on the next page. Mass number, I just highlighted this box because that's your math to it. Not a huge deal, I don't think. So the total mass, the atomic mass, here you go, here, this is what I was looking for. So it's a decimal point number, and that's because of these isotopes. So the isotopes are going to have, it's always, remember, it's always the same protons, but it could have different numbers of neutrons, and so it then would be different. Radioactive, I'm looking into showing you guys some pictures here. So radioactive tracers, I think I've got a picture of my brain to bring to school. All right, if you're also in AP Psych, you'll be learning about the PET scan in AP Psych as well. And then radioactive dating, we're going to look into this for some evolutionary stuff. And there's an article posted on Canvas about if fossil dating can really prove evolution. Optional, don't have to do it, but it's there for you. All right, energy levels of electrons. So what this is talking about, this is a great picture here, is you've got your nucleus, you've got your shells going on outside, okay? And so if your electron is sitting here, in order to move up, you have to gain energy or absorb energy in the form of heat or light or something. So then it moves up, and then if it has enough energy, it can move up even another one. Once it's up here, it makes the whole thing very unstable, and so it wants to go back down here. Think about climbing a ladder. If you're here at the bottom of the ladder, you have to use energy to get to that next rung, and then energy to get to the rung after that. But once you're on top of the ladder, maybe you're scared of heights and you're freaking out and you want to get back down again, so you're losing energy. Now, physics, we're just bringing everything in here. Once you move up your potential energy, if you fell from up here back down to here, it would hurt a heck of a lot more than if you fell from here. So as you go up and you're absorbing energy, you get to the top and you've got more potential energy, more chance to hurt yourself. And that's the same is true with electrons. That's 10th grade, kind of like the photoelectric effect, but hopefully remember some of that. And so that's what they're talking about with energy levels of electrons, but that's about it for that. Let's see. I'm not doing that. So these shells, you know how it is, they go around. Electron distribution of the chemical properties. What I need you guys to remember is 288 for me, please, in the first shell. As you can see in these drawings, this first shell can hold a maximum of 2. If we go to the second one, we have now that very first shell with 2. The maximum it can hold is 8. And if we go to this last one, you've got the first one that has 2, the second one that has 8, and then the third one that has 8 as well. So just please remember that, and I think we should be okay. I hope you remember that from 10th grade. And also please look at how these are drawn. These are exactly how I draw them in my class, where you've got everyone that's paired up. If we go back over here now, you draw the one shell and then the one electron. Now here, the 2 on the inside are paired because they're not going to pair. If you've got a second shell, the first 2 are paired, you're not bonding there. So on this outer one, you can see how now these are all alone, and you keep going around and around for 4, and then around, and you keep going until they're filled for 8. And that's the way I'm going to want you to draw it as well. Important. These are called electron distribution diagrams. I've never called it that myself, but that's okay. And I think there's one place where you have to draw these, and it's different than a Lewis dot structure or an electron dot diagram. I'll show you those guys in a minute. All right, what else? Orbitals. Don't freak out about this. As you're reading through this and it's like a PS1, PS2, all this stuff over here, don't freak out, okay? I did the work right here. I wanted to see for myself. I teach this in 10th grade chem, but I can't see this being on your exam. If we see it again come up in another chapter, I'll hit it harder. But for right now, just know that there's orbitals, and these orbitals are where the approximation, they're 90% sure that the electron is in here. The electron is moving way too fast in order for us to really know the location of it. But please, when you get here, don't freak out, because I would, but don't. All right. Then we're going to bonds. Oh, here. A lithium atom contains 3 protons and 4 neutrons. What's its mass number? So go back to that formula and do it up. A nitrogen has 7 protons, and the most common isotope of nitrogen has 7 neutrons. A radioactive isotope of nitrogen has 8 neutrons. Write the atomic number and the mass number of this radioactive nitrogen as a chemical symbol with subscript and superscript. So just how you saw them done in the book before, where it's got that top number and the bottom number, that's what they're looking for. How many electrons does fluorine have? You can just look at the periodic table and see that. How many electron shells? Oh man, okay. I don't want to do this. I didn't want to waste time bringing up a periodic table, but they're looking for fluorine right here. If you go across the top, these are the numbers of the groups that are together. These are your noble gases, so that means that they're unreactive because they have full outer shells. These are the most reactive group on the periodic table because they're dang close to being full. They're just 1 away. These are also very reactive because they're also very close to being 1 electron away from being completely full. So if you count 1, 2, leave out the transition elements. So 1, 2, 3, 4, 5, 6, 7, 8. You can say that this has 8 valency electrons, 7 valency electrons, 6 valency electrons, 5 valency electrons, 4 valence, 3 valence, 2 valence, and 1 valence. So that's the way I taught it when I taught 8th grade, just to say how many valency electrons these have. And if we've got that, then I think that would be very helpful for us. Okay, so how many valence electrons does fluorine have? Oh, how many total electrons? Dang it. Okay, go back to the periodic table. All right, so we know that it's got 9 protons, and because it's neutral on the periodic table, we know that it has to have 9 electrons. How many electron shells does it have? Let me show you a cool trick if you don't remember this. On this side going down, 1, 2, 3, 4, 5, 6, 7, that's how many shells it has. So we know that it's in 2 if we go across, so we've got 2 shells. All right. How many electrons are needed to fill the valence shell? Okay, they all want 8, except for that first one. We know it has 7, it needs 1 more. In figure 2.7, if 2 or more elements are in the same row, what do they have in common? Great question. Let's look at this. So, if they're in the same column like this, we know that they have the same amount of valence electrons. That's the important thing. If you're going across like this, we know that it's arranged by increasing atomic number, so increasing amount of protons, and so they just continue to increase by 1 for protons. All right. The formation and function of molecules depend on chemical bonding. So if you're a molecule, you're a covalent bond, and covalent bond means to share. And in a covalent bond, you can have a single, double, or triple bond. Nitrogen is going to make a triple bond. Oxygen is going to make a double bond, and lots of things make single bonds. Here's where Lewis dot structures came up, and let me draw you one really quick. So here is carbon. It's always so great when I draw on these things. A Lewis dot structure would be this. You've got the carbon in the center. The symbol for C is going to represent the nucleus with the protons and the neutrons and all the inner electrons. And so you can easily see that carbon has 4 valence electrons. All right, here they are bonding hydrogen and hydrogen, and if you have 2 hydrogens bonded together, it's called a diatomic molecule. And so here we have its 1 valence electron, and its one valence electron, and what happens is they share, so we circle it. And that's a hydrogen bond. All right, nitrogen. I think it's important to show you a triple bond and how that works for your worksheets. So what I'm going to do is when I get two nitrogens coming together, I'm going to leave the unpair electrons off to the sides, because I don't want to, oh, I'm out of my range, dang it. Okay, and then I've got two over here. This is bad. Okay, so I'm going to have this bond between these two. I'm going to have this bond